I'm Kelly Hammond, Senior Director for Robotics and Product Performance. And today I'm going to talk to you about what Intel is doing in robotics, some of the things we're doing to bring performance into what we do, and the brand new kit that we just released. First of all, before I dive in, I want everybody to just take a moment and just, in your mind, envision a robot, right? Any sort of robot. Maybe your favorite one. Okay. Now hold that thought. The origin of the word robot is humanoid. It was a 1920s play by a Czech writer, Karel Čapek, that coined the term robot. And in this play, the robot was actually far more human than even mechanical. And if you think about robots today, and what they are overwhelmingly not humanoid. So let's go talk. I'll talk about some of the robots that we're working with. Out of our imaginations, robots have evolved into a diverse array of form factors. These are robots that help us with manufacturing. They help us make things. They help us move things. They've evolved like a species even into a variety of form factors and also into automation. They're growing rapidly as well. The use of robots in places like Amazon's warehouse, for example, is growing very quickly, but again, not in humanoid form. And it's because our world is changing, and it has to change. We've been building infrastructure based on single products and infrastructure designed for a single workflow. And that doesn't scale. The world of today is built with infrastructure for flexible paths, things that you can grow over time to grow from small business to large business, to go from point A to point B and change where point A and point B are. The inflection point for all of this is computer vision. LiDAR, depth cameras, and particularly image recognition and the advancement of high-quality image recognition has made the robotic technology take off. It can do new things, as you can see here, like agricultural uses or retail. The ability for the robot to perceive its environment is fundamental to the changes that are happening in robotics. The other thing that's changing is time-based technologies. And I know there's a variety of people in SSP working on these. We have the real-time patches that have recently landed mainstream in the Linux kernel. We have time-sensitive networking and time-coordinated computing. And all these allow for a different kind of interaction. They allow robots to interact with each other, have a similar sense of time, as well as allow time-critical operations like functional safety so that robots can work with humans. So I'm curious now, what did that robot you imagined look like? Was it Johnny Five, or maybe Ava from Ex Machina, something from a movie? Or was it the robot that delivered your last Amazon order? Because the robots we're working on are not necessarily the robots that you see all the time. So what we're doing and why it matters to Intel is that this helps to drive data at the edge. When you put computer vision out there, you start sensing your world. And you create a vast array of data and bandwidth that drives Intel's data-centric vision. And as you can see, it's not for toys. While we do want to enable robotics for developers and developer systems, the kind of robots that we're targeting are in warehouses. They might be in retail. They might be a robotic shopping cart or a last-mile delivery. And the other thing is that we don't need to just do new products. one of the great things we're working on, and the great things about computer vision, is you can actually add it to existing robotics. And the way we're doing that is with the robot operating system. We've been working in ROS, and particularly in ROS2, for about 5 years. And actually, we're one of the founding members of the technical steering committee for ROS2. In terms of what Intel brings to robotics, we don't exactly sell robots, but we make all the critical technologies that need to come together to make robots, particularly the ones that drive compute. We bring together the software, like OpenVINO, and the model zoos that go with that, the accelerators, like Movidius X, the RealSense depth cameras, as well as both computing on both our CPU as well as GPU. In the future, we're looking to integrate some of the other technologies, like an RTOS for safety solutions, or edge server solutions. I'm going to dive into what we're doing to create performance, but in order to do that, I need to give you an overview of what ROS is and what pieces we're working on. The base of ROS is an infrastructure that you can build any sort of automation on. The blue here is where you see the parts that Intel's working on and where our focus areas are. Obviously, we build first on top of Linux. We use the Data Distribution Service, or DDS, as our primary layer because that's a production-hardened technology. This connects to the ROS middleware layer and the ROS client library, where we use these, particularly the C++, to wrap the other functions and other nodes and capabilities that Intel adds, which I'll get to next. While we work within and on top of the ROS2 core, our major contributions are in these areas. Mapping and planning, including navigation, is something we've taken a leadership in. As we started the ROS Technical Steering Committee and looked at the ROS2 code base, we realized that we'd never be able to make an autonomous robot without having good navigation. We also noticed that the original community was very fragmented. It had created fork after fork after fork of navigation solutions. So we've created a new navigation solution based on some of the best of the existing technologies with a flexible infrastructure so that we can encourage the community to create navigation solutions and build upon them, as opposed to continue to fork and diverge. Machine vision is core to what we do and core to our performance capabilities. This is where we do all of our inference and AI at the edge. And last but not least, robot arm control, which is something we've been working on for a little less than a year now, but where we are working towards adding all the computer vision capabilities into the more basic controls. So I'll build from the bottom up of what's in here. Of course, we start by adding the drivers. The biggest thing here is just to make sure that ROS2 has the core platform and hardware support to go run on Intel by default. So you get all the libraries. You get the Neural Compute Stick SDK from Movidius. You get the OpenVINO, so you can run on either CPU or GPU, as well as libRealSense. Machine vision is the #1 area and also the area we've spent the most time in since we've begun this project. And as part of that, that's meant that in the latest version, in the ROS2, we practically own the image pipeline. We have several maintainers, and we maintain several projects. And in that, we pull together all the different pieces. We actually got a really great compliment, actually a couple days ago, that was posted on LinkedIn, saying that it was a team that was building a demo off of what we did. And they said, unlike every other robotics solution, our image pipeline worked seamlessly out of the box. So for anyone creating a robot, they could build it with the RealSense camera, and the entire image pipeline works well and reliably without having to do anything else. Allows you to innovate. And we spend a lot of time with the object analytics, where you're doing all of your obstacle detection and avoidance. The next piece, as I mentioned a little bit before, is mapping and planning. This is where we have navigation, which you can do in both simulation as well as on a Turtlebot 3. The other pieces that are included in here are the capabilities to do autonomous navigation using technologies like SLAM so that you can build a map as you go dynamically. For our work in the robot arm control, we've recently been doing a lot with MoveIt. MoveIt is the top package to do robot arm control within the ROS2 system, ROS and ROS2. We've also partnered with our Intel labs, and we've productized some of their technology to integrate that in here as well. So we're bringing new capabilities here. And you can really think of what we do here as basically hand-eye coordination. We're taking all of that expertise that we have in the machine vision and using that to coordinate with the robot arm. Last, but certainly not least, are tools and documentation. So we contribute to several of the tools, but we also create tools, particularly performance tools. And I know just about every developer I know hates documentation, but we did it anyway. So, because it's the first thing that our customers ask for. And it's the first thing anybody new starting out asks for. So we've put all the documentation in there to get people started and to be able to use our products, our software. Last but not least is the simulation environment. And largely, we work on compatibility here, and we work with our other technical steering committee members to make sure that the simulation works well. Because whenever you're working with hardware, and you need to do rapid prototyping, simulation is your tool for that. You can't be agile in a pure hardware world if you have to create 10 different environments in the physical world when you can go and create them easily in the simulation world. Now that we've covered the basics, let me dig into the machine vision a bit more. Because this is where the advances that have been driving robotics in the past few years come from. And in particular, they're the biggest bottleneck when you look at your computing for robotics. The need to navigate, to identify objects, to do that AI, do that inferencing at the edge, that's usually one of the #1 loads on your computer. And also, slows things down. It can be a limiting factor in how fast your robot can go. So if you have an autonomous robot and you have a half-second delay, that's going to limit the speed at which they can go. So one of the most important things for us was to go through and optimize this pipeline. We started with RealSense. Originally, we had the full pipeline, all of the entire bandwidth of data pumping through the whole system. And the first thing we did was to split it out, because it's a lot of data that you get. So we split out between the raw image and the point cloud that gives you the depth information, because you actually need those to do different things, and you don't need to pipe them around everywhere. So that's the first improvement we did. Next was including OpenVINO. So it depends on what kind of system you're running on. But most of the systems that include any sort of integrated graphics, your object analytics are going to go faster on the integrated graphics. So, this includes that out of the box to give you better performance. Or if you're going to go for a smaller robot and build something a little more lightweight with maybe an Atom CPU, that's where you probably want to offload. And you can do that with the Movidius. And the Movidius neural compute stick is, with a little USB plug-in, is pretty easy for people to develop with, and then you can include it as part of the hardware. And we worked also on scaling that so that we have good scaling as you add more accelerators and more compute sticks. A big part of speeding this up was all about reducing the data to only the critical components. So the next piece was grabbing the detected objects and using just the detected objects for further processing. That allowed us to then localize the objects to either identify, perform an operation like identify the person's face, or also localize where they are and make sure that the robot could then avoid them and create a path around them. But I think the thing I want to get across in terms of what we did to improve performance is that we really took a systems view, and we benefited greatly from the fact that we work in open source, and that we've been able to work with so many of our Intel partners to create and to open source their drivers and software, because that has allowed us to submit patches to OpenVINO, submit issues and get fixes from Movidius. Because we work in ROS, we can work at the communication layer, as well as the object analytics and the packages that we already own. So the nice thing about this is when we put this all together, that's where we actually got the benefit, right? And that's really what makes it great for somebody to go out and use this solution, because they're not going to get this if they just used RealSense on its own and hadn't, with no other help or improvements. And then whatever comes next. We still have many different pieces within the ROS2 system that are student code. So there's a lot. We are working particularly with many of the other technical steering committee partners to harden that and to make things go faster and better and be more reliable to be built into product and scale to product. So I'm going to pause a little bit. That's kind of the overview and the deep dive into the technical pieces that we've created. But you can see if we were going to go try and talk to a customer and tell them, buy Intel, right? You saw my first picture of 3 different pieces of hardware and 4 different pieces of software and all these different things. So we've had some feedback too from some of the sales teams that that's challenging. You can say performance, but if you then give somebody a list of 25 steps to go get it, it's not the same. So what we did is made it easy. And that's where we created our kit. So on April 24th, we announced and released for the first time our robot kit. And what this does is it allows us to sell a solution, right? It's still based on ROS2. It's building from ROS2. It's all open source. It's the documentation and the build scripts. But it allows people to go and take everything, all those different pieces, and put them together. But most of them come, with all the instructions, it all comes together, and then they can innovate. And that's really what we want. We want people to be able to go create new use cases on robotics, not figure out how to plumb the infrastructure or the messaging. It really was about our core values as a team. We want to make it simple, make it performant, and make it open source. And that's what drove us to create this, which isn't maybe the typical path of an open source team. We still spend most of our time with ROS2, but we decided to make a kit. Here are the different pieces. Right? You get the Intel ROS and the ROS nodes. And this is where you think about ROS. You can think about ROS kind of like OpenStack, right? There's a ton of different pieces out there. So what we do is we just go grab the pieces that you need to get started. You can always add more. You can change more. But it gets you started. It includes all of the optimized libraries and all that performance optimization that I just showed you. All the tools, the visualization, the simulation, examples, and tutorials. Right now, it supports the autonomous mobile robot, the second one that you see there. And at the end of this year, we'll support the robot arm. It runs on an Intel NUC or IOTG's 80-link neuron board. It includes all the steps for setup, upgrade, the tutorials to help you learn APIs, build robot applications, include our optimizations or use our optimization tools, and simulate, debug, verify, all the things you need to do good in robotics. What this allows you to do, if you just build this out of the box, is create an autonomous mobile robot. You could have a robot for your warehouse, can run around and pick up your packages. It includes indoor mapping with SLAM, based on the RealSense, the ability to navigate point to point, either in simulation or in real environment, navigate with LiDAR or the camera, detect and localize 3D objects, and detect people using the deep learning model zoo. And it works with IOTG's RFP-ready kits. So these are open and readily available, one of which already includes ROS2 support, and who we are working with on kit support, as our kit already supports their hardware. So you can find us on GitHub. I encourage you to check it out. Give us a star if you like it. Even better, feedback. We'd love to hear what people think and any sort of ideas or features that they would like to see.